Right, we're looking at the third part of simple harmonic motion. We'll have a quick look at what this actually means. Now, what you'll notice, of course, is we're using a. I'm going to just change the name here because all this is actually is just a heading. All this column here is multiplying that column by the amplitude, which is 2. So if I just change that to 3, you'll see how the graph here on the right hand side changes to a maximum value of 3. If I change that to 10, you'll see how it changes to a maximum value of 10. I'm just going to keep that at 2 at the moment. It's, I think, clear enough for what we want to try and achieve here. If these two are obviously directly related to each other, this one and this one. The only difference between them is that they both, one is multiplied by its amplitude. Now this one is a little bit more complicated, and in fact what I've done on this one is I've just multiplied by omega, but just to make sure that we actually do use sine for this one, just a bit of annoyance in my mind there, get that to sine. I'm actually going to base it not on this calculation, which is what it's doing at the moment. It's using that calculation there instead. In fact, what I'm going to do is I'm going to show you how this is actually written to make it a little bit easier. So the equation, and I'm going to type it into the box. I'm just going to delete that one. Now you can now see that. So we have now differentiated this. So it's now a negative, and it's the amplitude times the omega times sine of the angle in radians. Now remember, the angle in radians is actually omega t. It's based on the previous one. So all I need to do here is copy that down. So just select it, and you can do it either by mouse or pressing the page down. Now what you'll notice very rapidly here is that it now becomes a negative number, and it should go to a larger value. So if we go and look at this graph and this graph, and we compare it to what we actually drew, you should see that this one, oops, just hit something with my mouse, this part here, I'm at the maxima. I'm now at 0 because of course I've gone to cosine into sine instead. So sine of 0 is 0, and you'll notice that the gradient is negative, which is what we were seeing before. Now you'll notice that the x-axis is based on the calculation where the maximum is amplitude of the oscillation multiplied by omega, the angular speed. So here we have exactly the same situation, but the graph is out of phase on this one here by pi over 2. Now we can now go to acceleration. Acceleration is based on this value here multiplied just again by omega. So what I've done in fact is just save myself that equation. So that equation there multiplied by omega is that equation there. I've just done a simplified version of that there. Press Ctrl C, page down, voila. If we now look at that graph, we'll see that it is pointing in the same direction. Sorry, we do have to change that. My apologies. Let's change that completely, because of course we're now going to cos again. So we can't do that rather simplified version that I did there. We have to go for something completely different. So start out for something completely different. I'm going to use this value here, very similar. So you have minus a. Right, I made something slight bug mistake on the previous one. I'm just going to correct that. So I'm just put the minus sign in there properly, and now we have the correct equation all the way down here. So as we look at this one, and let's go down here and have a look at the two graphs. We have the velocity graph and the acceleration graph, and the displacement graph. I'm just going to shrink the page a little bit. Hopefully you can still see it on screen. Zoom in if you can't. Right. I just want to talk about the locations here and how they differ from each other a little bit. So I've now got my annotation tool here, kind of a little drawing tool. So up here we have the maximum displacement. Here the acceleration is in the opposite direction, so it's pulling backwards. And at the same point at which the acceleration is pulling backwards, the displacement is maximum, the object is actually stood still for a fraction of a second. So if we were thinking of this as being, say, a spring, this would be at the point when the spring is at its very top. So if we have our little spring here, and here's the mass at the bottom of it, it is now compressed, and it's at its maximum displacement upwards. And just for a fraction of a second, pretty much infinitesimally small time, it is stood still. There's no velocity at all. The acceleration then goes to 0, so it's no longer accelerating. What's happening with velocity? Well, the velocity in this case is a negative, or we'll notice that the opposite is true here. The velocity is a positive. So in terms of locations, the velocity as its maximum, that would be when it's passing its equilibrium position. So as this is moving past this point here, it has got most kinetic energy, and then it's starting to slow down again until it gets to the bottom of its movement. So that is when it's at its maximum velocity, is when it's passing the equilibrium position here. What's happening to the displacement? Well, when that's at that point, the displacement is here. So it has no displacement. So you can actually compare that location, those two locations with each other, the velocity and the displacement, and you can see displacement is 0. That means it's at its equilibrium. We now go down and we look at when the acceleration is at its maximum. Just go up here. The displacement is at the opposite maxima, but the velocity is 0. So in this situation we have those two opposite. So this is now pulling backwards. Remember, acceleration and force are in the same direction, so the acceleration is trying to pull it backwards, back towards the equilibrium position, and the velocity at that point turns out to be exactly 0. So we can actually see on this graph here how those three relationships work together.